Water as a solvent. Water, or H2O, is a molecule where we have two hydrogen atoms connected by covalent bonds to a single oxygen atom. Now, from our periodic table, it is observed that the oxygen atom is slightly more electronegative than the two hydrogen atoms, which are slightly more positive. This induces a temporary dipole upon the molecule as a whole. Therefore, water is described as a polar solvent, where we have oxygen slightly negative and the hydrogen slightly positive. The aim of this investigation, or this report, is to test or determine how do substances dissolve, specifically in contact with the polar solvent of water. Now, soluble and insoluble substances in contact with water are affected both intermolecularly and intramolecularly. We will be showing or determining how water affects the inter and intramolecular bonds of the specific substances, and thus how this allows the substances to dissolve or not to dissolve. Hydrogen chloride, a polar molecular compound, is a diatomic molecule consisting of a chlorine atom combined with a single hydrogen atom through a single covalent bond. The chlorine atom is slightly more electronegative than the hydrogen counterpart. Since this is the case, a temporary dipole movement is induced within the molecule, with the chlorine being slightly more negative than the slightly positive hydrogen, and making the molecule polar and extremely soluble in water, a polar solvent. Upon contact with water, the weak covalent bonds between the two atoms are overwhelmed by the polarity and the bonds are broken. The slightly more positive hydrogen atom is attracted to the slightly negative oxygen atom of the water molecule, producing a hydronium ion, H3O. The chloride ion is independent of the hydronium ion and produces an ion on itself. Therefore, a hydronium ion and a chloride ion are produced when HCl combines with water, producing hydrogen chloride in its aqueous solution. Therefore, hydrogen chloride dissolves in water. Cellulose, an inorganic compound, consists of various molecules of alternating glucose and polysaccharide molecules linked by strong intramolecular forces between the carbon, hydrogen and oxygen atoms, and in turn the intermolecular forces in the form of hydrogen bonds connecting various chains of cellulose into a structured formation. The hydrogen and oxygen atoms from neighboring cellulose strands are attracted, arranged uniformly, hence forming a stable, hard, crystalline structure that provide the bundle of chains of cellulose with additional strength and stability. A non-polar molecule, this large and unyielding structure enables a molecule to be insoluble in water whilst attaining hydrophilic features. These bonds ensure this strong structure. Upon contact with water, the hydrogen and oxygen atoms of the cellulose are attracted to the respective oxygen and hydrogen atoms of the water, as seen in this model below. However, the hydrogen bonding that occurs between the two molecules are too weak to deteriorate the intra- and intermolecular bonds existing within the cellulose. The intramolecular bond of the cellulose is stronger than the intermolecular bonds formed by the water, and therefore cellulose refuses to dissolve in water. Thus, the H bonds that the cellulose molecule have is too strong to override the water polar molecules. Therefore, the water molecules are unable to separate the atoms from the cellulose chains, and thus the cellulose will not dissolve. Model evaluation. A three-dimensional model was used to visually and tangibly represent the manner in which hydrogen chloride molecule is affected when in contact with water. This model was effective in physically, visually and tangibly representing the covalent bonds existing within the molecule and how it is broken to form new bonds with water. It was successful in demonstrating the practical elements of the chemical reactions that occurs and has provided a simplistic understanding of the elements of the dissolving process. However, since the model was only a generalization of the actual molecule, and since it did not show any valence electrons, the model may have been incomplete or inaccurate, leaving assumptions. A two-dimensional model was used to represent the insolubility of cellulose in contact with water. The model was effective in visualizing the manner in which the strong inter- and intramolecular bonds of cellulose are insoluble in contact with water. It enabled the visualization of the polymer in a concise and unsophisticated manner, and therefore enabled a greater sense of understanding of the chemical processes behind the reaction. However, since the model was only two-dimensional, existing in only two planes, the model lacks a detailed and thorough understanding of the tangible representation of the bonds existing between the cellulose atoms and polymers, hence limiting the understanding of how it reacts with the polymer. This concludes our video.